Well, welcome back to our course on algorithms and data structures. We'll continue on in this area where we've been now talking about stacks. And so last time we gave an introduction, and now we're going to be talking about stack implementation. So I think this will be an interesting thing for us to explore. So for stack implementations, here is the information that we have in the textbook. So we'll be talking about three different implementations, a linked implementation, an array-based implementation, and a vector-based implementation. And then there'll be a few other things that we'll refer to into the Java class library and using a vector and what that implies for implementing the ADT stack. So two of the ADT stack descriptions in this chapter use techniques like the ones we use to implement the ADT bag. So we'll use in turn a chain of linked nodes and an array to store the stack entries. And then we will introduce the standard class vector as part of the Java class library and use an instance of vector to represent a stack. So hopefully this will be pleasantly surprising by the simplicity and efficiency of these implementations. So here we, in terms of the linked implementation, we have a couple of operations. We have push, we have pop, we have peek, and then we have the head of a linked list is easiest, fastest to access, and so that's typical for a stack. So moving on here, now we have this figure. So as we start to be talking about a linked implementation, each of the operations push, pop, and peek of the ADT stack involves the top of the stack. If we use a chain of linked nodes to implement a stack, where in the chain should we place the stack's top entry? If we have only the chain's head reference, we can add, remove, or access its first node faster than any other. Thus, the stack operation will execute fastest at the first node in the chain, which is illustrated in the figure. Note if you use a chain of linked nodes to implement a stack, the first node should reference the stack's top entry. So here's an outline of the class. The linked implementation of the stack has a data field top node, which is the head reference of the chain of nodes. Default constructor sets this field to null as an outline of the class appears in this chart. So each node in the chain is an instance of the private class node that is defined within the class link stack. This class has set and get methods and is like the one that we saw for the ADT bag in chapter 3. So let's talk about adding to the top. We push an entry onto the stack by first allocating a new node that references the stack's existing chain, as shown in figure A here on the chart. This references top node, the head reference to the chain. We then set top node to reference the new node, as in figure B on the bottom, and thus we have that, and that's just giving you a visual of how this actually works. Here is a definition of the method push, just for reference. Okay, let's talk about removing from the top. We pop or remove the top entry in the stack by setting top node to the reference in the first node. Thus, top node will reference what was the second node in the chain, as shown in the figure. Moreover, the original node will no longer be referenced, so it will be deallocated, since we also want the operation to return the stack's top entry before it is removed. The method pop is something that we need to make sure that we specify here. And here we have the methods for both peek and pop. So, and then there's other classes, is empty and clear. And so here we're showing the implementations of those, fairly straightforward code. Well, let's get into the array-based stack implementation. If we use an array to implement the stack, where should we place the stack's top entry? If the first location of the array references the top entry, as shown in the figure we'll show in a minute, we must move all of the entries in the array anytime we add or remove a stack entry. We can have more efficient stack operations if the first array element references the bottom entry of the stack. The top entry of the stack is then referenced by the last occupied location in array, and we'll see this in a minute. And this configuration allows us to add or remove stack entries without moving other items in the array. That's one disadvantage of a typical array-based implementation, does not apply here. Here is the figures that we're referring to, and you can see how that works as we get a chance to be looking in more detail at the array-based stack implementation. Note if you use an array to implement a stack, the array's first element references the bottom of the stack. The last occupied element of the array then references the stack's top entry. So that's a good way to do it with an array implementation. So here's an outline of the class. The array-based implementation of the stack has as data fields an array of stack entries and an index to the top entry. The default constructor creates a stack with a default capacity. Another constructor lets a client choose the stack's capacity. And so we're seeing that in the figure. So to indicate an empty stack, we assign a -1 to top index as its initial value. This choice allows push to simply increment top index before using it when placing a new entry on the array. So we have the couple of methods here. So adding to the top, the push method checks when the array has room for a new entry by calling the additional private method ensure capacity. If necessary, ensure capacity resizes the array thereby avoiding a stack that has no room for a new entry. The push method then places the new entry immediately after the last occupied location in the array. Note that ensure capacity is similar to the ensure capacity method in the resizable array bag, which we talked about in chapter 2. Both private methods double the size of the array after it becomes full. So we're also showing the method push. And so we can see that there's two things here that are noteworthy. When ensure capacity does not resize the array stack, push is big O notation 1 operation, since its performance is independent of the size of the stack. However, resizing the array is a big O notation N operation, so that the array, when the array is full, the performance of the push degrades to big O N. If this happens, however, the very next push is big O 1 again. To be fair, all push operations should share the cost of the occasional resizing of the array. That is, we amortize the cost of doubling the array size over all additions to the stack. Unless we must resize the array many times, each push is almost big O 1. So now let's talk about a remove function. So if we're removing from the top, the popper operation like the peek retrieves the top entry in the stack, but then removes it. To remove the stack top entry as shown in the figure on what we just showed, we could simply decrement the top index. And now as in figure 5, in the A on the top shows that the simple step would be sufficient, since for other methods it would behave correctly. For example, given the stack pictured in the above here, peek would return the item that stack references. However, the object that previously was the top entry and has now been returned to the client would still be referenced by the array. No harm will come from the situation if our information is correct. To be safe, pop can set the stack top index to null before decrementing top index. And so the figure B illustrates the stack in that case. So here we're looking at retrieving the top and removing the top. So the first on the top, the operation peek either returns the array entry at the top index or throws an exception if the stack is empty. The operation is big O notation 1. For removing the top operation like peek retrieves the top entry in the stack, but then removes it. To remove the stack's top entry, we could simply decrement the top index. This simple step would be sufficient since the other methods would behave correctly. For example, given the stack that we were just showing in a picture, peek would return the item that stack references. However, the object that previously was the top entry and now has been returned to the client would still be referenced to by the array. No harm would come from this situation if our implementation is correct. To be safe, POP can set the stack top index to null before decrementing. Peek, like peek, POP is a big O notation 1 operation. Okay, let's talk about the vector-based stack implementation. One way to let a stack grow as needed is to store its entries in an array that you resize as you did in the implementation of array stack. Another way is to use a vector instead of an array. A vector is an object that behaves like a high-level array. A vector's entries are indexed beginning with 0, just like an array entries, but unlike an array, a vector has methods to set or access its entries. You can create a vector of a given size and it will grow in size as needed. The details of this process are hidden from the client. If we store a stack entry in a vector, we can use the vector's methods to manipulate the stack's entries. We'll show this figure in a second here. So here's the figure. So the figure shows a client interacting with the stack by using the methods in stack interface. The implementation of these methods in turn interacts with the vector's methods to produce the desired effects on the stack. So just a couple things. First, a note for the Java class library, the class vector. The Java class library has a class vector in the package java.util. A vector is analogous to a resizable array if the elements are indexed beginning with 0. You work with a vector by using its methods. So let's talk about the outline of this class. A class that implements the stack begins by declaring a vector as a data field and allocating the vector in its constructors. Thus, we can provide an important statement prior to the class definition as we're showing in this listing. Okay, I think there's a lot of different methods and things that you can be using within the class vector. And so I won't go through those now, but just be mindful of that. And you can learn more about the vector in the online documentation for the Java class library. Here is the method for adding to the top. We use vector's method add to add an entry to the end of the vector, that is to the top of the stack. And for retrieving the top, we retrieve the stack's top entry by using the vector's method last element. And for removing the top, we can remove the stack's top entry by using the vector's method remove. The argument is the method to this method is the index of the top entry in the vector, since the entry is at the top of the stack. This index is 1 less than the vector's current size, stack.size. And for the rest of the classes, the remaining public method, we have one is titled isEmpty, and the other one is clear, invoke analogous vector methods, and we're showing those in here. Okay, that's going to end this lecture. Thank you very much.